Welcome to Lesson 3.3, Creating Custom Datasets. Overview. Most fine-tuning projects live or die by the quality of their training data. A brilliant model architecture trained on mediocre data will always lose to a simpler model trained on excellent data. In this lesson, you'll learn how to build high-quality training data from scratch. Use LLMs to generate and scale that data, and apply augmentation techniques to squeeze more signal out of what you have. Budget about 45 minutes. This is intermediate territory, but everything builds on what you already know. Learning objectives. By the end of this lesson, you'll be able to create custom datasets manually. Use LLMs like Claude, GPT, and Gemini to generate training examples at scale, and apply data augmentation to increase diversity. You'll also understand the quality versus quantity trade-off, which is one of the most misunderstood concepts in fine-tuning, and know how to build domain-specific datasets, version control your data, and recognize exactly when adding more examples stops helping. Methods for creating custom datasets. The first approach is manual creation, writing examples by hand. This is the right choice for small datasets in the 50 to 500 example range, or any situation where quality is non-negotiable. It's slow, but every example is exactly what you intended to be. The second approach is LLM-generated data. You prompt a capable model to write training examples for you. This scales well into the 500 to 5,000 example range and is ideal for bootstrapping a dataset quickly, though it requires careful prompting and human review. The third approach is data augmentation, taking examples you already have and systematically transforming them to create new ones. This is your best tool for increasing diversity and balancing categories without starting from scratch. The fourth approach combines all three with a quality control layer on top. This is the right strategy when you need a large dataset, thousands of examples, and you can't sacrifice reliability. Think of it as a production pipeline rather than a one-time effort. Method 1. Manual dataset creation. Font week creation. Before writing a single training example, the most valuable thing you can do is write down what you're actually building. This documentation block defines the project as a customer service bot for TechStore, specifies the target interaction types, orders, returns, and technical support, locks in the tone as professional, helpful, and empathetic, and records the constraint that responses must cite accurate company policies. This isn't busy work. When you're on your 50th example and wondering whether a response sounds right, this document is what you check against. It keeps every example pointing in the same direction. Here's the conversation template that every training example will follow. It's a dictionary with a messages key containing a list of role tag terms. The first message is the system turn. It tells the model who it is and how it should behave: a helpful TechStore customer service agent, professional, and empathetic. The second message is the user turn, a placeholder for the customer's question. The third is the assistant turn, a placeholder for the ideal response. This structure matters because it mirrors exactly how chat models are trained to process conversations. Every example you write will slot into this template, which keeps your dataset consistent and directly compatible with the chat format your model expects. Next, define your categories. This list captures the 5 types of customer inquiries the bot needs to handle: order status, returns and refunds, product information, technical support, and billing issues. Each category maps to a distinct class of customer problem, and the comment sets a concrete target, 20 to 30 examples per category, for a total of 100 to 150 examples. That target isn't arbitrary. It gives you enough variety within each category for the model to learn the pattern without so much repetition that you're wasting effort. Define your categories before you write a single example and you'll never end up with 80 order status examples and 3 billing months. This code builds the actual dataset file. You define your conversation examples as a list of dictionaries, each one following the message template from before, with real content filled in for the user and assistant turns. Then the code opens a file called textstore_dataset_v1.jsonl. For writing, iterates over every example and writes each one as a single JSON object on its own line. That's the JSON-L format, one complete JSON record per line, which makes it trivially easy to stream large datasets without loading everything into memory at once. The final print confirms how many examples were written. If that number doesn't match what you expect, something silently failed upstream, so always check it. Alongside the dataset itself, this code creates a companion metadata file. The metadata dictionary captures everything you'd want to know about this dataset 6 months from now: the project name, version number, creation date, total example count, a breakdown of examples per category, the system prompt that was used, and a notes field flagging what still needs work, in this case more technical support examples. This gets saved as textstore_dataset_metadata.json. Think of it as the label on the jar. The dataset file contains the data. The metadata file explains what the data is, where it came from, and what its known gaps are. Future you will be grateful. Method 2. LLM generated data. The core appeal of LLM generated data is speed and scale. You can generate hundreds of examples in minutes, and because you're prompting a language model, you get natural variation in phrasing and scenario framing automatically. The catch is quality. The model will occasionally produce responses that are plausible sounding but subtly wrong, inconsistent with your style guide, or just repetitive in ways that aren't obvious until you read them carefully. LLM generation is a force multiplier, but it multiplies your prompting skill, not a replacement for it. This prompt is the core of your LLM data generation strategy. It asks for 10 high-quality customer service dialogues, specifies the output format as JSON-L with system, user, and assistant roles, and defines 3 categories: order tracking, product returns, and technical troubleshooting. The system prompt instructs the generating model to adopt a professional, empathetic tone. User messages are specified to be natural and varied, sometimes including order numbers, sometimes not. Assistant responses must provide concrete, actionable steps. The output requirement of valid JSON-L is explicit, which reduces the chance of getting back prose you'd have to reformat. After running this, you either send it to the Claude API directly or paste it into ChatGPT, then save whatever comes back for validation. Here's what a well-formed generated example looks like in JSON-L. The system message establishes the assistant's role and tone. The user message presents a realistic, specific problem, an order placed 5 days ago that hasn't arrived. The assistant response demonstrates exactly the behavior you want: acknowledgement of the frustration, a concrete next step, and an offer to escalate. When you review LLM-generated output, this is your quality bar. Each example should read like something a genuinely helpful human agent would say, not a corporate script, and not a vague non-answer. Any example that doesn't meet that bar gets edited or discarded before it touches your training data. This prompt drives variation generation, one of the highest leverage techniques in dataset construction. You provide seed examples like "where is my order" and "I want to return a damaged product." Then ask the model to generate 10 variations of each. The prompt explicitly requests variation in formality and allows for occasional spelling mistakes. That last detail is important. Real users don't type in perfect prose, and if your model only ever trains on clean, grammatically correct inputs, It will be brittle when it hits the real world. The output comes back as a JSON array, which you can iterate over and add directly to your dataset. One seed question becomes 10 training examples in seconds. This snippet constructs a batch generation prompt programmatically. The user_questions list holds a set of typical customer queries. The prompt string assembles the system context, professional, empathetic customer service agent, and then uses chr10 join to format the questions as a numbered list inside the prompt. Building prompts this way, with code rather than by hand, means you can swap in a different question list and regenerate without rewriting anything. The output is specified as JSON-L, one entry per question, which drops directly into your dataset pipeline. This is the pattern you'll use whenever you want to generate responses at scale from a fixed list of inputs. This script automates the full generation pipeline using the OpenAI API. It imports the necessary libraries, reads the API key from the environment, and defines a generate_examples function that takes a category name and example count, constructs the appropriate prompt, and calls either GPT-4 or GPT-3.5-turbo depending on your budget. The function then passes the response line by line, and this parsing step is where things can go wrong. If the model returns a line that isn't valid JSON, the script logs a warning and skips it rather than crashing. That's intentional. LLM output is occasionally malformed, and a robust pipeline handles that gracefully. Valid examples get collected and written to a JSON-L file, with a final count printed as confirmation. Always check that count against what you requested. A quick note on cost. With GPT-4, generating 10 examples runs about 1 cent, which puts 500 examples at roughly 50 cents and 5,000 examples at about $5. Claude tends to produce more verbose, higher quality outputs at comparable pricing. Neither is expensive for the dataset sizes you'll work with in this course. The real cost is your time reviewing the output, not the API bill. Here's the equivalent call using the Anthropic API. You import the library, initialize the client with your API key from the environment, then call write single quote client.messages.create write single quote with the model name clause 35 sonnet 202411022 max underscore. The response content comes back in write single quote message.content write single quote comma, which you print to verify the output before passing it into your dataset. The structure is almost identical to the OpenAI call, which means once you've written one, writing the other takes about 2 minutes. The choice between them mostly comes down to output style. Claude tends to be more detailed and verbose, which can be an advantage or a nuisance depending on your use case. Method 3. Data augmentation. Data augmentation starts with a single high-quality example and systematically generates variations from it. Here, the original example is a simple translation task. Translate hello to Spanish with the output hola. From that one seed, you create a list of variations. How do you say hello in Spanish? What's the Spanish word for hello? Spanish translation for hello, and so on, all pointing to the same correct output. You've just turned one training example into 5 without writing any new content. For tasks with a fixed correct answer, this is essentially free data. The model learns that the same underlying question can arrive in many different forms, which directly improves its robustness on real inputs. The generate_paraphrases function automates this process for any instruction. It takes an example and a target count, then constructs a prompt asking the model to produce that many paraphrased versions, varying formality, varying length, but preserving the original meaning. The output is requested as a JSON array, which gives you a clean list to iterate over. The actual API call isn't shown here, But this is exactly where you'd insert your OpenAI or Anthropic client call from the previous section. The function returns a list of paraphrased instructions, each of which pairs with the original output to form a new training example. Run this on your 10 best seed examples and you've tripled your dataset before writing a single new response. Here's a different flavor of augmentation, changing the context rather than the phrasing. The original example asks the model to summarize a paragraph about Python. The variations keep the instruction identical but swap in different programming languages, JavaScript, Rust, Go. The instruction structure stays the same, only the subject matter changes. This teaches the model that the summarization skill generalizes across domains rather than being tied to a specific topic. It's a subtle but powerful technique. When your model later encounters a summarization request about a language it's never seen in training, it's far more likely to handle it correctly because it learned the task pattern, not just the specific instances. The add_realistic_errors function introduces controlled noise into user messages. It defines a dictionary mapping correct phrases to their common erroneous equivalents. Don't becomes don't, I'm becomes im, you. The loop iterates through these pairs and applies each substitution with a 30% probability, so not every message gets every error. The result is a dataset that includes the messy, informal, typo-ridden inputs that real users actually send. If you train exclusively on clean text, your model will be silently fragile. It'll work perfectly in demos and degrade in production. Sprinkling in realistic errors during augmentation is cheap insurance against that failure mode. This augmentation technique converts a single turn exchange into a multi-turn dialogue. The original example is a brief two-message conversation. A user asks about the return policy and the assistant answers. The augmented version extends that into a realistic back and forth. The user follows up with questions about the time window, whether they need the original packaging, and how long the refund takes. Each follow-up gets a specific, helpful response. Multi-turn dialogues are harder to write but far more valuable for training because they teach the model to maintain context across a conversation rather than treating each message in isolation. If your target application involves any kind of ongoing dialogue, you need examples like these in your dataset. Quality versus quantity. When to stop adding data? This graph shows something counterintuitive that trips up almost every first-time fine-tuner. As you add more training examples, performance improves, but the curve flattens. Eventually, adding more data produces almost no measurable gain. That plateau is the signal to stop. The mistake people make is assuming that if 500 examples gave them a 10% improvement, 5,000 examples will give them 100%. That's not how it works. You get the biggest gains early, and each additional example contributes less than the one before it. Understanding this curve is what separates people who iterate efficiently from people who spend a week collecting data and wonder why their model didn't get better. Here are the concrete numbers to guide your decisions. For format teaching tasks like generating valid JSON, 50 examples is your minimum, 100 is solid, 200 is excellent, and beyond 500 you're getting diminishing returns. For teaching a style or personality, aim for 100 to 500 examples before expecting real consistency. For injecting new knowledge the model doesn't already have, you're looking at 500 to 5,000 examples. Complex reasoning tasks, chain of thought, multi-step problem solving need the most data, with the sweet spot between 3,000 and 10,000 examples. These ranges assume high-quality examples. Drop the quality and every threshold shifts higher. The single most important principle in dataset construction: one excellent example outperforms 10 mediocre ones. Before you add any example to your dataset, run it through this mental checklist. Is the input clear and unambiguous? Is the output correct and genuinely helpful? Does this example represent the behavior you actually want? Is it free of typos and errors? Is it consistent with your other examples in tone and format? And critically, does it add something new, or is it just a near duplicate of something already in the dataset? If an example fails any of these checks, fix it or cut it. Mediocre examples don't just fail to help, they actively teach the model the wrong thing. Two clear signals tell you to stop adding data. First, you're writing examples that feel like slight variations of things already in the dataset. You're not adding new patterns, just more instances of existing ones. Second, your model's performance on the validation set has plateaued across multiple training runs. Two clear signals tell you to add more data. First, the model is consistently failing on a specific type of input that you can identify. Second, your validation loss is still decreasing, meaning the model is still learning and hasn't saturated the dataset. If the model starts overfitting, performing well on training examples but poorly on new inputs, that's also a signal to add more diverse data, not to reduce it. Building domain-specific datasets. Domain-specific datasets require extra care, and the medical domain is the clearest example of why. This example structures a conversation about hypertension with a system message that establishes two non-negotiable constraints: provide accurate information and always recommend consulting a healthcare professional. The assistant's response covers the definition, risk factors, and management strategies for hypertension, substantive and useful, but explicitly not a substitute for professional advice. Notice the metadata section. It tags the example by domain, subtopic, difficulty level, and sources. That sourcing field isn't decorative. For medical, legal, or financial content, you need to be able to trace every factual claim back to a reliable reference. If you can't source it, don't include it. The legal domain follows the same pattern. The system message establishes the assistant as a legal information resource, not a legal advisor, and instructs it to recommend consulting an attorney for anything case-specific. The example conversation covers what an NDA is, its key elements, and common use cases. The metadata adds a jurisdiction field, which matters because legal concepts vary significantly between countries and even between states. A response that's accurate for US law may be misleading for UK law. Tag your examples with jurisdiction from the start. Rope-fratting that information onto an existing dataset is painful, and training a model on jurisdiction-unaware legal data is a liability you don't want. Version control for datasets. Version control for datasets. Version control for datasets. Version control for dataset versioning solves a problem that will absolutely bite you if you ignore it. You train a model, improve the dataset, retrain, and the new model is worse, but you've already overwritten the old dataset. Version control gives you the ability to track exactly what changed between training runs, roll back to a previous dataset if new data hurts performance, document how your dataset evolved over time, and collaborate without overwriting each other's work. Treat your datasets with the same discipline you'd apply to source code. The save_versioned_dataset function handles this automatically. It takes a list of examples and a version node string, generates a timestamp, and uses that timestamp to create a unique version identifier, something like v_2024. It then builds a metadata dictionary capturing the version string, creation time, example count, and your notes. The dataset itself is saved as a JSON-L file with the version identifier in the file mem. The metadata gets its own JSON file alongside it. The function prints both fail lines on completion. This means every time you save a dataset, you get two files, the data and its documentation, both uniquely named so nothing ever gets overwritten. For Git-based versioning, the workflow is straightforward. Navigate to your datasets directory, run git init once to initialize the repository, then add and commit your initial dataset file with a descriptive message, something like initial dataset 50 customer service examples. When you expand to a second version, add and commit the new file with an updated message reflecting the new example count. Running git log DROE online gives you a compact history showing every commit hash and message. That's your audit trail. If a new dataset version makes your model worse, git checkout hash restores any previous version instantly. This is the minimum viable version control setup, and it takes about 5 minutes to configure. Hands-on exercise. Here's your first hands-on exercise. The task is to build a dataset for a homework helper chatbot that explains math concepts to high school students. The requirements: at least 10 examples using the conversational format with system, user, and assistant turns. Cover 3 topic areas: algebra, geometry. Every assistant response should walk through the solution step by step, and the tone should be encouraging and educational. The template below gives you the structure to fill in. This code defines the homework underscore helper list with one complete example, a student asking how to solve a two-step equation and the assistant walking through it methodically. Then it saves the dataset to homework underscore helper underscore dataset.jsonl, writing each example as a single JSON line with ensure underscore ASCII =sign false to handle any special characters like mathematical symbols correctly. Your job is to fill this list out to at least 10 examples across algebra, geometry, and trigonometry. The structure is already there, you're just writing content into it. Here are 3 more example ideas to get you started. The first covers the Pythagorean theorem. A student asks what it is, and the assistant explains the formula, what each variable represents, and works through a concrete triangle example with real numbers. Notice how the response doesn't just state the formula and stop. It shows the calculation step by step, which is exactly the behavior you want the model to learn. The second example could cover factoring quadratics, the third sine and cosine basics. Each one follows the same pattern: a student question that feels natural, and an assistant response that teaches rather than just answers. That distinction, teaching versus answering, is the key quality signal for this dataset. Now a variation exercise. Take this single example and create 5 variations from it using the augmentation techniques you just learned. The original example is a unit conversion task. The instruction is convert 5 kilometers to miles, and the output is 5 kilometers is approximately 3.11 miles. 1 kilometer =sign 0.621371 miles. Notice that the output includes the conversion factor. It's not just the answer. It's the answer plus the reasoning tool that lets you verify or extend it. That's a quality signal worth replicating in your variations. Create your 5 variations by working through these 4 strategies. Paraphrase the question itself, change the numeric value, change the units, try meters to feet or miles to kilometers, and add context like I'm planning a run and need to know the distance. Each strategy produces a meaningfully different training example while keeping the underlying task identical. Here's what a complete solution looks like. The variations list contains 5 entries. The first paraphrases the original. How many miles is 5 kilometers? The second changes the number, 10 kilometers to miles. The third reverses the direction, miles to kilometers. The fourth adds context. A runner planning a 5K race who needs the distance in miles. The fifth changes the unit entirely, kilometers to feet. Each output includes the conversion factor alongside the result, consistent with the original. One seed example has become 5 distinct training examples, different phrasings, different numbers, different contexts, all teaching the same underlying skill. That's augmentation working exactly as intended. Key takeaways. Here's what to carry forward from this lesson. Start small. 50 to 100 high quality examples will outperform 1000 mediocre ones every time. Use LLMs strategically to scale your dataset, but always review the output before it touches your training pipeline. Augmentation through paraphrasing and context variation is your highest leverage tool for increasing diversity cheaply. Version your data from day one. The 5 minutes it takes to set up Git versioning will save you hours of confusion later. In domain-sensitive areas like medicine, law, and finance, every example needs a disclaimer and a citable source. And always watch your validation performance. When the curve flattens, stop adding data and start improving quality instead. Quick reference: Dataset creation workflow. Here's the complete workflow condensed into a repeatable sequence. Define your use case and goals before writing a single example. This is your North Star for every quality decision. Choose your format: instruction output pairs or multi-turn conversations. Write 5 to 10 seed examples by hand. These are your quality anchors. Use an LLM to generate variations and new examples at scale. Review and edit every generate output before it enters the dataset. Apply augmentation to add diversity. Shuffle the full dataset and split it 80/20ths into training and validation sets. Save with versioning. Run a small test training to identify where the model still struggles. Then iterate. Add more examples specifically targeting the failure cases you found. Each pass through this loop produces a better dataset and a better model. Knowledge check. Before moving on, make sure you can do each of these things with confidence. Create a custom dataset manually with at least 10 examples. Use an LLM to generate training examples from a well-crafted prompt. Apply paraphrasing augmentation to multiply your seed examples. Explain why one excellent example is worth more than 10 poor ones, and be specific about why. Set up Git versioning for a dataset directory, and identify from a validation loss curve when you've hit the point of diminishing returns and should stop adding data. Assignment: Why fight so kera. Your assignment is to build a custom dataset for your own project. Choose a domain: customer service, education, code assistance, whatever aligns with what you're building. Create 50 to 100 examples total. Write 10 to 20 seed examples by hand. Use an LLM to generate 30 to 80 more, and review and edit every single piece of LLM output before it goes in. Apply augmentation to add roughly 20% more examples through paraphrasing. Save everything as version 1.0 in JSON-L format with a companion metadata file. The deliverables are 3 files. Your dataset as my_project_v10.jsonl with at least 50 examples, a metadata file as my_project_v1.0_metadata.json, and a README documenting what the dataset teaches, how it was created. That last document is the one future you will be most grateful for. What's next? You've built your custom dataset. The next problem is making sure your model can actually read it. Chat models don't just consume raw message dictionaries. They expect the conversation to be formatted according to a specific chat template that varies by model family. Get that template wrong, and your training data becomes noise. Lesson 3.4 covers exactly how to apply chat templates correctly, and it's one of the most common places where fine-tuning setups silently break. Don't skip it. Additional resources. For further reading, the Awesome Dataset Creation Repository is a curated collection of tools and techniques worth bookmarking. OpenAI's data generation guide covers their recommended practices for synthetic data creation. Anthropic's prompt engineering documentation is the best reference for getting high-quality outputs from Claude. For augmentation techniques beyond what we cover here, search for the academic literature on NLP data augmentation. There's a rich body of work on back translation and synonym replacement in particular. And if you're working on a team and need collaborative data labeling with a quality review workflow, Agila is an excellent open source option. Mark this lesson complete when you've finished your assignment dataset. This diagram shows the full data pipeline from raw sources to a finished dataset. Raw sources, web pages, local files, documents feed into a cleaning and normalization step that strips inconsistencies and irrelevant content. From there, the data gets formatted into instruction pairs, then deduplicated and filtered to remove neat duplicates and low-quality entries. Tokenization and validation confirm the data is correctly formatted for your target model. The final split goes 90% to training and 10% to validation, and the output lands as either a JSON-AL file or a Hugging Face dataset object. Each step in this pipeline exists because skipping it causes a specific predictable failure downstream. The deduplication step alone can dramatically improve training efficiency. Duplicate examples don't add information, they just inflate your training time. This comparison chart scores 5 dataset creation methods across quality, speed, and cost on a 1 to 5 scale. Manual annotation scores highest on quality but lowest on speed and cost. It's thorough but expensive in time. LLM-generated data using models like GPT-4 scores well on both quality and speed, making it the most practical choice for most projects at this scale. Augmentation methods like paraphrasing score moderately across all 3 dimensions. They're not the highest quality, but they're fast and cheap relative to what they produce. Filtering an existing dataset scores lower on quality, but is quick and inexpensive. Template-based synthetic generation is the fastest and cheapest option, but quality is the trade-off. The right choice depends on your constraints. If you have time, start with manual examples. If you need scale quickly, reach for LLM generation. This radar chart visualizes dataset quality across 6 dimensions: completeness, consistency, accuracy, relevance, volume, and diversity. The green outline represents a high-quality dataset. The red dashed line represents a poor dataset, weak on nearly every dimension. What this chart makes concrete is that dataset quality isn't a single number. A dataset can be accurate but not diverse, or large in volume but inconsistent in format. Both will hurt your model, just in different ways. When you audit your own dataset, run through each of these 6 dimensions explicitly. The gaps you find there are exactly where you should focus your next round of augmentation or manual writing. This pie chart shows a recommended distribution of instruction types for a general purpose training dataset. Question answering takes the largest slice at 25%, reflecting how often models are asked to retrieve and explain information. Summarization comes in at 20%, code generation at 18%, classification and extraction each account for 12%, and creative writing rounds out the chart at 7%. If you're building a specialized model, your distribution will look different. A coding assistant should weight code generation much higher. But if you're building something general, this distribution gives you a useful starting target. An imbalanced dataset will produce a model that's noticeably better at some tasks than others, which is either a feature or a bug depending on your use case. This flowchart shows the manual creation workflow as a loop, not a straight line. You define your task scope, write examples, send them through peer review, and then run a quality check. If they pass, you augment them with variations and they enter the final dataset. If they fail, you go back and revise based on the feedback. The loop structure is the important insight here. Manual dataset creation isn't a one-pass process. It's iterative. Your first examples will be good. Your 10th revision of those examples will be better. Budget time for at least one review cycle on every manually written example before it goes into training. The quality check step is where most of the real value gets added. This diagram shows the LLM data generation pipeline in detail. It starts with 5 to 20 human-written seed examples. These are your quality anchors. Those seeds feed into a prompt template that instructs the generating model on format, tone, and content. The LLM, GPT-4 or Claude then produces a batch of 100 to 1000 outputs. Those outputs go through automatic validation checking for correct format and appropriate length, then through deduplication to remove near identical entries. What comes out the other end is a clean, diverse dataset ready for training. The seed examples are the most important input in this entire pipeline. Weak seeds produce weak generated data regardless of how good your prompt template is. Write your seeds carefully. This table summarizes 6 data augmentation techniques with their use cases and risks. Paraphrasing rewords instructions while preserving meaning, high value, low risk, but watch for subtle meaning shifts. Back translation converts text to another language, and back, adding lexical diversity at the cost of occasional quality degradation. Synonym swapping replaces keywords with synonyms, useful for low resource tasks, but prone to domain mismatches if the synonym doesn't fit the technical context. Instruction expansion adds detail to existing instructions, increasing robustness. Response variation rewrites answers in different styles, promoting tonal diversity but risking factual drift if the rewrite changes the substance. Negative samples provide intentionally incorrect answers for classification tasks, which is essential for RLHF training. Each technique has a specific use case. Don't apply them indiscriminately. Match the technique to the problem you're trying to solve. This graph makes the quality versus quantity trade-off concrete with 3 performance curves. The high-quality dataset curve rises steeply and plateaus at a strong performance level. Even 500 high-quality examples can outperform models trained on far larger but noisier datasets. The medium quality curve rises more slowly and plateaus lower. The low quality curve barely moves even as the dataset grows to 50,000 examples. The implication is direct. If you're spending time collecting more data and your model isn't improving, the problem is almost certainly quality, not quantity. Before you write your next 100 examples, go back and audit the ones you already have. Fixing 10 bad examples will do more for your model than adding 100 mediocre new ones. Here's the recommended folder structure for a production quality dataset project. The top level directory is named after your domain, My Domain Dataset. Inside you have a readme.md documenting what the dataset is and how to use it, and a dataset_card.yaml containing structured metadata. The data subdirectory holds 3 JSONL files: train.jsonl at 80% of your examples, validation.jsonl at 10%, and test.jsonl at the remaining 10%. The scripts directory contains 3 Python files: generate.py for creating new examples, validate.py for checking format and quality, and stats.py for computing distribution statistics. The raw_sources directory. This structure separates concerns cleanly. Data lives in one place, code lives in another. Documentation is at the top level. Set this up before you write your first example, and you'll never have to reorganize later. This diagram shows dataset versioning as a branching progression. Version 1.0 is your initial dataset. Adding augmentations produces version 1.1. Applying a quality filter, removing examples that don't meet your bar, produces version 2.0, a major version bump because you've changed the character of the dataset, not just its size. Expanding with domain-specific data produces version 2.1. Deduplication and final validation produce version 3.0, which gets tagged in Git and pushed to Hugging Face. The pattern here is deliberate. Minor version bumps for additive changes, major version bumps for changes that affect what's already in the dataset. This convention makes it easy to understand, at a glance, how different two versions are, and whether a model trained on one should be retrained on the other.